In this work, we propose synergizing contrastive learning and optimal transport for effective unsupervised domain adaptation for 3D point clouds. An important aspect of achieving cross-domain adaptation is to leverage the model trained on simulated data where it is easy to get annotations and generalize it to real-world data for which obtaining labels is a cumbersome task. This would also benefit in controlled simulated environments. For example, a chair's visual representation can vary significantly between a game and architectural design software in VR environments. If a model is trained on a synthetic dataset and evaluated on its test set, it works exceedingly well. However, we see a drastic performance drop if we evaluate it on a real-world dataset. In the unsupervised domain adaptation setting, given source and target data with only source labels, the task is to do well on the target data, thus bridging the gap between both the domains. In the synthetic to real-world setting, the task of UDA is challenging as the real-world data often has many problems like missing parts, severe holes, or even backgrounds in the input scan. The core of our idea is to synergize contrastive learning and optimal transport. Given source and target data, contrastive learning first produces initial class clusters in the source and target domains individually. Subsequently, our OT module better aligns the same class clusters across domains. We also leverage the idea of multimodality within the source and target domains. Given a point cloud, we use its multi-view renderings as another modality in our contrastive learning module. We do so to incorporate correspondence between 3D and 2D features. They also help to capture silhouette and surface boundaries that are harder to derive just from point-wise distances. Also, they can be seen as a form of data augmentation. Given source and target domains, with only source data having class labels, a point cloud is taken from both the domains. This point cloud is augmented with two transformations, T1 and T2, which are compositions of transformations picked randomly from a set of predefined transformations. The original and augmented point clouds are then mapped to a d-dimensional feature space using a 3D encoder, producing their respective embeddings. Along with these 3D features, we also extract multi-view renderings and get aggregated 2D features from an off-the-shelf image encoder. Contrastive loss is then applied between the augmentations of the point clouds and between the averaged feature and 2D features. For the OT loss, the original point cloud embedding and the target class prediction is passed. Finally, a supervised classification loss is applied on the known source labels and their predictions. Self-supervised losses are applied on both modalities, where these losses aim to pull the same class closer in the representation space. For the optimal transport loss, the cost function is defined as the sum of difference between point cloud features and the difference between original source label and predicted target label. Given the cost function, we first optimize for the optimal coupling matrix. The optimal coupling matrix is then used as in the final OT loss function, which aims to align same classes across domains. The total loss is a sum of all these losses, where 3 are self-supervised and 1 is supervised by the known source class labels. Our method achieves state-of-the-art performance on GraspNet-10 dataset. It also achieves a best average performance on the PointDA-10 dataset. We also examine the decision boundaries of our learned models. We fit an SVM and consider a 1 versus rest strategy to visualize the decision boundaries. The decision boundaries get smoother and more compact as we add individual modules to our method. The ablation study shows that each module effectively contributes in order to achieve the best adaptation performance. To conclude, we propose a novel UDA method for 3D point cloud classification that synergizes working of contrastive learning and optimal transport. We advocate using multimodal inputs for 3D 2D feature alignments. Our method achieves state-of-the-art results on GraspNet-10 dataset and the best average performance on PointDA-10 dataset. The perform experiments and ablation studies show the importance of each module. Thank you for watching.